Hello everyone. In the two previous videos we discussed the forward kinematics, analytical forward kinematics using the Dennevit-Hartenberg or DH convention. But that is not the only way to acquire forward kinematics equations. So DH convention is a very systematic approach, but it requires initially carefully setting up the frames, the coordinate frames attached to the rigid bodies in a robot. There are other methods that might not need, that initial careful setting up the axis, so you can just choose the orientation and the location of the coordinate frames kind of arbitrarily, not perfectly arbitrary, but kind of arbitrarily. And so you have to keep track of what you're doing. So it's not going to be as systematic as DH, but initially they might look quite more convenient and simpler than the DH method. There is no table to form and nothing. All you need to really care about, for example, in this vector addition method, is writing everything back to the base frame. That's all you need to do. So, as I said, there are different methods, and the second method I'm going to talk about is called the vector addition method. So, what do we do here? So, let's say here I have this articulated 3D OF robot. So you have three rotary joints. Okay, the first one is rotating about this vertical axis, and the other two are about this horizontal axis. I have some fixed geometry in this robot, which is including D0, D1, D2, D3, D4, and D5. These are all constant distances, and none of them is changing. There is no prismatic joint here. And the variables are the joint rotations, theta 1, theta 2, and theta 3. So what we want to do is to solve this problem as forward kinematic using a new method called vector addition method. So here, what I will do, I will set up my coordinate frames kind of at my convenience. So if we go down here to the base of the robot and look, my origin of the base frame, I set it right here at the center of the, at the bottom and at the center of the first joint. So we call the base frame here I, or if you want, you can call it frame 0. It does not matter really. So here xi, yi, and zi are these three guys that you can see. This is xi, this is y of I, and this is z of I. Okay, and they are, or you can actually, you might use this one because, yeah, they are the same thing, z1 and zi, but here. So this is xi, yi, and zi. These are, an I again here means inertial, because this frame does not rotate. It is attached to the ground, and you can count on it as inertial frame. So these are xi, yi, and zi. Then we go to the center of the joint. So here there is some physical displacement d0. And then we set up our next coordinate frame. This is x1, y1, and z1 that you can see in blue. Okay, so the difference between them is really just an offset of d0 along the zi direction. That's all it is. Okay, there is nothing else. It just counts for this physical displacement of d0. If it's negligible, you can just put them on the top of each other. Or you might just bring your inertial frame and put it here at the center and avoid this frame number 1, because really this frame number 1 is doing nothing extraordinary beyond what the inertial frame is doing, okay? It's not rotating, it's not doing anything, it has just some offset d naught from frame I. So it's not really such a necessary thing to add that as an extra frame, but here is just to give you the idea that, well, you can put your frames wherever you want, in whatever direction, and they can be free rotating, not rotating, and so on. And then you go frame 2, you put it at the center of this joint. So you kind of see why it is added in this case here is also because the coordinate frames like 1 and 2 are at the center of the joint. And since inertial is put at the bottom, so here that's why frame 1 is also considered. It doesn't mean it's mandatory really, but it's just to be similar to the other joints. Then we have frame number 3, which is again at the center of the next joint. And finally, we have the end effector frame. Okay, so this orange one is frame number 3. And finally, we have frame E here, which is the end effector. So clearly you see here, I have not called the inertial frame, I have not called the first frame 0, I have called it frame I. And I have not called the last frame N. I called it what? Like in this case, it should have been frame number 4. I called it the E frame. So just wanted to tell you that E here is the same as 4, and I here is the same as 0 that we had in the Denavit-Hartenberg. We can still call them those. It's not going to affect anything here. It's just a notation. Good. Now, as you can see, clearly the rules of DH are not observed here. Like, for example, if you look, let's say this X here, X number 2 and Z number 1, you see they are skew, and it's not said that they intersect each other, they don't. Or here, again, if you look, for example, this X and this Z, they intersect, they are perpendicular, that's good. The next X and this Z also do, but clearly you see the place that it is violated. In the first one also they're good. The only place that X perpendicular to previous Z and intersecting it is going from frame 1 to frame 2, that you see that rule is not observed. But if I could change any of these, is that going to change the way that I solve this problem? No, not really. All it does, it might change some parameters, as we'll see. So for example, if in this orange frame number 3, I change X and Y, so make X3 to the right and Y3 out of the board, and then Z3 probably have to change direction downward, then the rotation here, that is rotation about y-axis and theta 3, would be rotation about x-axis and theta 3. But since x is referring to the axis of actuation here, it doesn't matter what you call it. By the way, as you see, the axis of actuations are not also called z, right? So you see here the axis is y, here the axis is y, here it is z. So many of the things of the Denavit-Hartenberg are not observed here, and that's the advantage of this method. That does not force you really to choose a specific directions as z or x and put origins at the specific locations. You're kind of free. Now, what we need is to find the position of point E, or origin of E, with respect to what? I, correct? So I can write it as d of, if I want to go with the same notation as Denavit, this is d of E in frame I with respect to I, correct? This is what I need to find out, and I also need R of E with respect to I. Okay, so these are the two things that I need to find in general as a function of theta 1, theta 2, theta 3, and then these d values that are coming from the geometry of the robot. Good. So here I use a similar notation to what I did in the past for omega. If you remember in the video where I talked about Euler angles and projecting angular velocities of the Euler angles, I used a notation like this. If you remember, I said omega of, let's say, 2 with respect to 1 written in frame I. This is a notation that I used over there, and I said this is what? This means the angular velocity of frame 2 with respect to frame 1, but it is written along what? It is written along the axis of frame I. So you write this omega to 1 as so many units times xi plus so many units times yi plus so many units times zi. Correct? You're writing it along the axis of the inertial frame, okay? Or, for example, this very same thing, you can write it about frame 1. What does this mean? It means whatever this entity is here, this omega of 2 with respect to 1, is just a vector, correct? Whatever it is, I'm going to write it as so many units times x of 1 plus so many units times y of 1 plus so many units times z of 1. So this is a vector, this guy. This is a free vector. I can write it along any axis that, along the axis of any frame that I desire. So, okay, I'm just trying to tell you the meaning of here these subscripts and superscript. So this is the new frame with respect to old frame, and this is the reference frame. Okay, so if I want to put the whole thing for you as a single notation, this is how I describe it. That if I say in general R of old or new frame with respect to the old frame written about the axis of what? Reference frame. Right? So this is a new notation that I'm going to use to basically denote a free vector R that is from one vector measured in the other with respect to the other. I just write it along the axis of some reference frame. Okay, so this is a new notation. So therefore, this d of e with respect to I, which is the position vector of end effector with respect to the origin of frame I, this should be written in about along the axis of which frame? Well, of course, with respect to I. Right? Everything has to be, the vectors have to be written along the axis of frame I so that I can use them for forward kinematics. Right? So this is matching that notation. Good? Fine. Now, note that here I'm not going to write R that way, and you might say, what about this R? Do you also need a superscript on the back for that? No, because R is not a vector, R is a matrix. Okay, so that's good enough. So let's focus on the position. What is this position? D of E with respect to I written in I. How can I get that? Well, for the moment, let's forget about this I thing. Okay, let's make life easy. Say just d of E with respect to I is what? Well, it If I want to show it here as a vector, it goes from what? Goes from origin of I to origin of E. So let me use some vector and write here if I can. So there's this vector. Now here I did a little bit of cleaning and got rid of those different colors for different axes, just trying to make it a little bit cleaner. And now if I want to get this vector that is exactly what I need here, d of E with respect to I, if I want to get this vector in black, what I can do is to get these four vectors instead. The first one, instead of going from I to E directly, it first goes from what? Goes from I to 1. So it is like d of 1 with respect to I, and then add it to, now what? The next one goes from the origin of 1 to origin of 2. So it goes something like this, right? And that you can write it as d of 2 with respect to 1. Agreed? And then what? The next one will be basically going from origin of 2 to origin of 3. So something like this, which you can call d of 3 with respect to 2. And finally, you can bring in, let's say, the last one, which goes from origin of 3 to origin of 4, like that. You can write it d of E or 4. In this case, we call it E, not 4, with respect to 3. Agreed? So this is what you do. You break the big vector into the addition of the vectors that are going from the origin of one frame to the origin of the next frame. If I add these four vectors, small vectors together, I should be able to get what? The d of n effector in the inertial frame. Okay, so let's look at the first vector, d of 1 with respect to I. If we zoom in here, what is this vector in orange? So what I'm doing, I'm moving a distance of d0 along the zi direction, correct? If you want, I can add here these indices here, so you know what is what. So this is what z1, this is y1, this is x1, this is xi, this is yi, this guy is zi. So along the zi, I'm moving a distance of what? d0. So I can write it down here, and I can say that this is equal to a distance of d0 in the direction of unit vector zi. Correct? Now, note that here, frame I is completely stationary. Okay, frame I is absolutely stationary. It doesn't rotate, and it is attached to the ground. What about frame 1? Okay, frame 1 is attached to what? Just like the DH method, it is attached to the rigid body that is basically coming next to it, although in DH is most of the time you cite probably toward the end of the link, but here this frame 1 is physically rigidly attached to this member here, this guy. So this guy in orange, it has frame 1 rigidly attached to it. So frame 1 is rotating with that member with angle theta 1 about the I frame. Okay, so frame 1 does rotate. Okay, and it is d naught unit in the zi direction. Good. So that first one is rather clear. Now, the second one was now d of 2 with respect to 1, that blue vector. How could I write it? Well, for that, I need to move a distance of d1 plus d3 in the direction of z1, this guy, up, and then also a distance of d2 in the negative direction of y1, and no motion along x1 because x1 is out of the plane. So now you might say, why don't you consider that, for example, d2, a motion along yi, why do you consider it along y1? And d1 plus d3, why don't you considering along z1, why don't you considering along zi? Now, for the case of z's, in this case, it's not going to make any difference, but the case of the y's, it does. Why? Because as I said, frame 1 does rotate with this member in orange, with this kind of, whatever you want to call it, this Z-shaped member or S-shaped member, whatever you want to call it, it is rotating with that. So when theta 1 is in effect, after a little bit of rotation, your x1 is going to look like this, and your y1 is going to look like that. The same thing with this member. It is going to rotate, and so your y1 and yi are not going to be the same direction. And the displacement is definitely along this y1, which is opposite to this member, because as I said, your member is now going to look like this. For example, this is going to rotate too. Okay, so this displacement d2 clearly is opposite to y1, not yi. So it's better that we are writing everything with respect to the axis of frame 1, not with respect to the axis of frame I. Okay, so here, if I want to write it, I should write it as what? It is going to be plus, as I said, it is negative d2 units about y1 or along y1, and then plus d1 plus d3 along the z of 1. Now the rotation theta 1 is not going to affect the direction of z1. z1 and zi are the same. So here you can even write it as zi, but since I wrote this one in 1, let me write this one in 1 too. And then plus what? Now plus, now I go over the red vector, which goes from origin of 2 to the origin of 3. So here, this vector, as you can look at it, it is d4 units in the direction of this guy here, and this one, you know, it is z2. So this is z2, y2, and x2. So this is d4 units in the direction of z2, which is already affected by angle theta 1, and now this frame 2, okay, this frame 2 is attached to this member in red as well, so it is also rotating with angle theta 2 about the y2 axis, okay? But the direction of this zt is, and this distance d4, z2 and d4, they are always going to determine how I go from origin of 2 to origin of 3. So for that red vector, I can write it as d4 times z of 2. And finally, as you can see, frame 3 now that is attached to this member in purple, which goes from origin of 3 to E, this guy is rotating with angle theta 3 about y3. And if you want to go from origin of 3 to origin of E, you need to go a distance of d5 about z3. So if you want to write that, you have to write it as plus d5 times z3. Okay, so if you add these four vectors together, that is d of e with respect to I. Now, if I want to write this into a matrix format, right, I can write this as what? I can write this as vector 0, 0, d naught. And here the reference for me are xi, yi, and zi. Good. Plus what? Plus, what can I write this one for? Or, yeah, I guess that's a good way to write it. Or you can write it as, well, I'm just trying to see if I can write it in a nice format for you. So I can write this as 0, 0, d0 times xi, yi, and zi. Okay, I'm just trying to write it nicely for you. Plus, how can I write the blue vector? The blue vector, this whole thing is what? It is like 0, negative d2, and then d1 plus d3 times x1, y1, and z1. Plus, what's the one in red? It is 0, 0, d4 times x2, y2, and z2. And finally, the purple is plus 0, 0, d5 times x3, y3, and z3. Right? So I can write it in a nice matrix way, or vectors here actually, this way. Good. Okay, now the question is, can I add these vectors together now? Can I add this one to this one to this one and to this one and get what I need? The answer is no, because they're all written along the axes that are different, right? Each one is written along a set of unit vectors that are different from the rest, and you cannot add apples and oranges. The same thing here. If you look, what I really have, d of 1 with respect to I, as you can see, is written in frame I. d of 2 with respect to 1 is written in frame 1. d of 3 with respect to 2 is written in frame 2. And d of 3 with respect to 3 is written in frame 3. And since the reference frames here for each one of these vectors is different, I cannot simply add them together and get what I need, which is all written in frame I. Right? Remember, I needed everything in frame I. So I need to make sure that only the first one matches the left-hand side in terms of the reference. I need to make sure that this 1 is somehow turned into I, this 2 is turned into I, and this 3 is turned into I, right? Or in other words, here, all of these guys here, this one, this one, this one, they are also somehow written in terms of xi, yi, and zi. Then yes, I can add similar vectors that they're all written in the same base, in the same reference. I can now add them together. Well, the question is, you see here, I have d of 2 with respect to 1 written in 1, which is this guy here. This one. how can I convert it into d of 2 with respect to 1, but written in I? That's what I need. How can I do that? Well, since this one is written in frame 1, this is written in frame I. And how do I go from I to 1? I go from I to 1 by what? By rotation about zi with angle theta 1. It's a rotation z and angle theta 1. And you know, if you want to go from the new frame to the old frame, all you need is to multiply it by rotation matrix of R of 1 with respect to, in this case, I, not 0. If I had this rotation matrix, I could multiply it, and that would give me what I really need, correct? But what is that? I just told you. It is the rotation z with angle theta 1, which everybody at this point knows how to calculate. It's a fundamental z rotation matrix with angle theta 1. If I multiply it by this vector, that should give me what? That should give me this one, which is what I need. So instead of just directly adding this to that guy, what I need is to multiply this, pre-multiply this by this rotation matrix. Good? So I can replace that now and say, hey, this is equal to this 0 and 0 and the naught. Add this to what? Multiply, I can write them as column vectors if I want to add them as well. Multiply this by a rotation, what? Let me write it this way. By a rotation z and angle theta 1, multiply this by this guy here. This one is now going to be what? This is now going to be exactly what I need. This is d of 2 with respect to 1 projected back into I, correct? Which is r of 1 with respect to I times d of 2 with respect to 1 written in 1. Okay, so now we can go to the third term here. And if you look at the third term, what we really need is to write d of 3 with respect to 2 in I, to project it along the axis of I, while what we have here, this guy 0, 0, d4, that's d of 3 with respect to 2, correct? So if I multiply it by the rotation matrix, that can take me from frame 3 back to I, that is going to get me what I need. So here I need to multiply it by a rotation matrix, this 0, 0, d4. Okay, if I multiply this by a proper rotation matrix, so this is d of 3 with respect to 2 in 2. If I multiply it by rotation of 2 with respect to I, that gives me d of 3 with respect to 2, but written in I. And what is r of 2 with respect to I? Well, r of 2 with respect to I is r of 1 with respect to I times r of 2 with respect to 1. R of 1 with respect to I is clear. That's rotation z with angle theta 1. I have that one. So that is already determined. And now, how do you go from 1 to 2? Is there a rotation involved between 1 and 2? And you clearly see, yes, there is. Right? So now what you have is a rotation of y and then angle theta 2, correct? That's what you have. So the next rotation here is going to be move this a little bit to here. And then I can move also this guy a little bit. Right? So I need to multiply it by a rotation of y and angle theta 2. And finally, this last one, which is r of e with respect to 3, that is written in 3, if I can convert it back to I, then I have everything that I need. So I need to multiply it by a rotation matrix, which is 3 with respect to I, and then, as I said, multiply it by this 0, 0, d5. Correct? So this one is d of I with E with respect to 3 written in E. If I can multiply it by the rotation matrix of 3 with respect to I, that gives me d of E with respect to 3 projected back in I. Okay, so for here I need the rotation matrix of 3 with respect to I, which is rotation of 1 with respect to I, times rotation of 2 with respect to 1 times rotation of 3 with respect to 2. And I have 2 of them. So I have the rotation z and theta 1, which is 1 in I with respect to I, times rotation of y and theta 2, which is 2 with respect to 1, and then 3 with respect to 2. If you look here, 3 is rotating with angle theta 3 with respect to 2. So that is going to be rotation matrix of y with angle theta 3. And you see the rotation is about the y-axis again here, y3. Okay, so if you multiply all of this together and add them, that is going to be the result. And for that, you can use Matlab here, right? So since I mentioned it several times, let me show you one time here how I'm going to define these all symbolically, multiply them together, and get you the result. Okay, so here is Matlab. I put this on my second monitor. I define every parameter that I need in it. So I say sims of what I need is D0, D1, D2, D3, D4, and D5. And then I need, let's call it T1, T2, and T3 for theta 1, 2, and 3. That's all I need. And I have a rotation 1 in I, which is a rotation z matrix with angle theta 1. So it is going to be cosine of T1, negative sine of T1, and 0. Then the next row is going to be sine of T1, cosine of T1, and 0, and then 0, 0, 1. And never suppress it. Always make sure that is exactly the matrix that you want. So don't use a semicolon at the end of the line. That's perfectly right. The next one is a rotation of 2, 1. Correct, which is a rotation y with T2, and rotation y is like cosine of T2 followed by a 0 and sine of T2. And then you have 0, 1, 0, and then negative sine of T2. a 0 and cosine of t2. So it is like this. And finally you have R32, which is just like this. It's a y rotation, but the angle is T3, theta 3. Okay. So that's this guy. And now everything is set for me to type the formula. So it is equal to 0, 0, and d naught plus R1I times 0, negative d2 and d1 plus d3, then plus R1I times R21 times 0, 0, d4, and finally plus R1I times R21 times R32 times 0, 0, and d5. Okay, and this is the result. As you can see, okay, it's a big thing, and I can bring it all out and write it somewhere here into my notes. See if I can use a big font. Not big enough. Maybe this one. And you clearly can see that right now. Okay, so that is the result here. d0 plus t1 plus d3 plus d5 cosine of t2 times t3 minus sine t2, t3. And you know you can always simplify this as cosine of t2 plus t3. So you can write it as c23. Okay, and then when you have, for example, here, this you cannot write much about it. Not that you can't, because if you factor out cosine of theta 1 out of it, the remaining of it looks like S23. So it is like C1 S23. Then also here, if you look, that's similar thing because there is again a sine T1 factored out, so it is going to be S1 times S23, and this is C23. So if I want to write it in short notations in a nice way, it is going to be D5 times C1 times S23 plus D2 times S1 plus D4 times C1 S2. The next term is D5 sine 1 sine 2 3, and then minus D2 C1, then plus D4 times S1 S2, and finally you have D0 plus D1 plus D3 plus D5 times C23. Okay, so this is if you write the whole thing in short notation. So let me get this out of the way, what I got from Matlab, and here we pretend that we did it all by ourselves very fast without the need for a software. You're really good with algebra, correct, and linear algebra, of course. And this is my d of the end effector with respect to base as written in base. Okay, so this is my position of the end effector with respect to the inertial frame. Good. This is my first result here. And then I can also calculate the rotation matrix of the end effector with respect to base as well. And clearly you see that the rotation matrix, if you want to go from the E with respect to I, well, what you need is you have to look at E with respect to 3. So E and 3, there is no rotation involved between them. What you have is 3 with respect to 2, which comes from theta 3, 2 with respect to 1, which comes from theta 2, and 1 with respect to I, which comes from what? Theta 1. E with respect to 3, there is no rotation. If you see the x's, the y's, and the z's are aligned. So you can say that my rotation matrix, which is E with respect to I can write it as rotation of 1 with respect to I times 2 with respect to 1 times 3 with respect to 2 times E with respect to 3. And as I said, the last one, it is an identity matrix. Okay, this one is an identity matrix. There is no rotation involved. This one was the rotation Z and theta 1. This one was rotation Y and theta 2. This one was rotation Y and theta 3. So all you need is to simply multiply these together and get your rotation matrix also as a 3 by 3. So again, we can do that with symbolic. And all you really need is this one here. That's all. So you multiply it and you get your result. And as always, you can go ahead and take it back to Matlab, to OneNote here, and then write it in short notations, right? And then pretending that you did it. Didn't get any help from Matlab. I'm just kidding. But yeah, if you look here, if you can see, there is a cosine theta 1 common between them. The remaining of it is cosine of T2, T3. So it is going to be C1 times C23. That's this element. The next one, so this is gone. The next one is just simply negative S1. And the next one is, if you factor out CT1, that's S23. So this is going to be C1 times S23. Okay, and then you go with this guy here, where sine T1 is common. So it's going to be S1 times C23, followed by cosine of 1. And then the last one, if you look, sine T1 is again common between them. So this sine of theta 1 times S23. And the last one here is negative of S of 23. followed by a 0, and followed by a C23. Right? So this is my rotation matrix of E with respect to I. And clearly it's not any fundamental matrix because you have a Z and a Y multiplied together. So it's not going to take the form of a Z or a Y alone. Okay, and this would tell you exactly how the axes of the end effector frame can be written about the axes of the base frame, and what is the coordinate X, Y, and Z of the end effector written or along the axis of X, I, Y, I, Z, I with respect to the origin of frame I. So you see, I could get my equations very well. And you see here that this guy here is a function of what? Everything involved in it. If you look, there is C23 and there is C1. So yes, all three angles are showing themselves here into the position. And here again, you clearly see this is all three angles again involved. So in this case, the three angles are involved in both position and orientation of the end effector with respect to base. Okay, they are effective on both of them. As well as, again, you see the geometric distances, D0, D1, 2, 3, all the way to D5, they are all showing themselves in the position, but clearly none of those is showing in the orientation. Because it's just the angles that determine the rotation matrix, the displacements, whether they are variable or constant, they have no role whatsoever in the orientation. Okay, so hopefully you can see how this method can easily be used with arbitrary setting of your coordinates and just projecting everything back into the iframe using appropriate rotation matrices, adding all of the entities now that they're all in the same base. Now you can easily add them together and get what you really need in here. Now, there is one other thing that I wanted to talk about very fast, and maybe if you're just so curious about how I went from here to here, really. So the idea is clear, not that one, maybe this one. How I went from here to here. Right? It's quite clear what I did. I just used the rotation matrix, but probably some of you are saying, well, here you used a row matrix. What happened here? You are using a column matrix. What's going on? Why did you convert your row matrix into a column matrix? Well, row vector into a column vector. What happened? Right? And that's not such a hard thing to show here. So what you have here is these are these vectors, if you see, x1, y1, and z1, and my goal is if I can write them into the terms of xi, yi, and zi, correct? How can I do that? So what I have is x1, y1, and z1, right? Is there any way that I can write them as something times xi, yi, and zi? Correct? Is there any way that I can write it as anything like that? And the answer is sure, you can. You just need to know each one of these ones, these axis ones, is how many of the i's. So what you really need is like this. x1 dot xi, that's the component of x1 along xi, and then x1 dot yi, and then what? x1 dot zi. These are the components of x1 along each one of those. So if you just multiply these numbers by xi, yi, zi, that will give you what? X1. And then you can do a very similar thing for y1 and z1. Correct? So here, let me just write it very fast. This is y1, not y2. There is no y2 here. So this is what you have. And now you might say, what is this? Well, if you look at the columns of this and the rows of this, you see it is the same as your rotation matrix of 1 with respect to I, but what? The transpose of it, correct? Because if you remember, in the rotation matrix of 1 with respect to I, each column was all x1, right? The next column was all y1 projected. The next one was all z1 projected. But here, the first row is x1, the second row is y1, the third row is z1. So this is R of 1 with respect to I transpose, okay? Good, so far okay? Now, what can I write this as? What is this one? Well, not that one. Let's go back here to this previous equation so I show you what happened. Guess it's here, yes. So what am I doing? Instead of this guy here, instead of this one, I should write what? R of 1 with respect to I transpose, correct? Times what? Times xi, right? Just look at this one. R of 1 with respect to I transpose times this, correct? So let's write it down. Agree? And what is this? What is this term? This is the same as this one, except it's transpose of that, right? So now do you see what I did? Yes? So this is what I did. Instead of writing it like this, 0 negative d2 and d1 plus d3, instead of me writing it this way, times those x1, y1, and z1, I wrote it as what? I wrote it as the rotation matrix of 1 with respect to I, transpose of it, times this, and for that I also wrote that one as its transpose. As you see here, I transpose that guy. So let me make sure I'm doing it the right way. Yes. So let's bring this here. wrote it like this. But now, instead of this, what I can do is I write this as a column vector, if you don't mind, and say the transpose of that. So I can write it like this. Right? This is what I did. So you can write it this way. Now look at here. If you look here, I have the product of two things that are transposed. Both of them are transposed. So this I can also write as what? Can also write it as, you know, from your linear algebra, that A times B, the whole thing transpose, is what? It is B transpose times A transpose, if you know, right? So here, this is BA transpose. I can reverse the order and then take transpose of the whole thing. So I can write it as R1 with respect to I times this guy the whole thing transposed times xi, yi, zi. And that's where, if you look, this term here is this guy here. Right? So that's where it is coming from. Just wanted to explain to you what happened that my row vector became a column vector, whereas that R1 with respect to I came from behind it and multiplied by it. So just wanted to do a little bit small practice on your linear algebra. But other than that, the method is clear. How we set up the axis is up to us. And if we know how to project vectors, this method could be very easy. Okay, thank you so much for your attention. See you in the future lectures.